Alrighty, so homework 14, properties and types of solids. For each of the following compounds, determine the type of solid that it forms. Identify the bonds or the forces in the solid. Sketch a sample for each. So, most of these, actually, I think most of these you could get from pretty much the paper that's got this. Like, versus to draw a diamond, you're going to draw something that looks like this. Copper is going to be similar to the platinum. It will just be copper instead. Let's see the different types here. So diamond, you're going to follow the network covalent solid look. Specifically, it's a three-dimensional network covalent solid. Copper, just copper, copper on copper. Copper is a metal. I'm going to make this a metallic solid. Calcium oxide comes from those two ions put together. So this is an ionic solid. Sugar, CHO, non-metal, 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 a bunch of non-metals up in here. That is indicative of a molecule, right? So this is a molecular solid. And make sure you draw me some absolutely beautiful pictures here. Which would be expected to have the lowest melting point temperature and why? So if it has low melting point, that's saying that it's has, like, it's being I'm going to say held together weakly. Because if it's only weakly held together, then I don't have to put in very much energy to melt it. So the network covalent one, covalent is a type of bond. So that's going to have a pretty strong melting point. Other ones that are really strong, ionic solid. This one is ionic bonding, and we've got full charge on full charge. So that's going to be really, really strong. Molecular solid, this one is the one that's entirely held together by IMFs within the molecule. So out of all of these, I'm going to expect sugar, because molecular solids have really low melting points. Let's see what else. I feel like I'm missing something. Oh, just for your own reference, if you're wondering what I mean by high and low, to get a diamond to melt from a solid to melting, you have to crank up the temperature to 4,000 degrees Celsius. Really freaking hot. Water boils at 100, and we've got to get this to 4,000. Yeah, right. To get copper to melt, you would have to crank it up to 1,000. Calcium oxide, 2,000 degrees Celsius. And to get sugar, just plain sugar, no water, sugar on the stove to melt would be 186. So obviously there's your difference, is those IMFs. There's no way you would know these values, by the way. The AP test doesn't want you to memorize stuff like that. It just wants you to be able to say, oh, this one would be the lowest because it's held together by IMFs. But I thought it would be interesting for you to actually see these numbers, so I looked them up. Which is expected to conduct electricity. If you are conducting electricity, you have moving electrons. I guess you could say moving charges because electrons have a charge. However you want to think about that. Let's see, we know that metals conduct electricity, right? Because they have the sea of electrons that are moving around. So that one's gonna conduct electricity. And the only other one that has moving charges would be the ion, because it has the 2 plus and the 2 minus. But this is only going to conduct electricity sometimes if those charges are able to move. We would get those charges to move one of two ways. We either have to melt it so that it's in a liquid form, or you could dissolve it in water so that it's aqueous. So those are the only two that could potentially conduct electricity. Elemental boron is extremely hard, nearly as hard as a diamond, and has a melting point of 2300 degrees Celsius. It is a poor conductor of electricity at room temperature. What kind of solid would you expect for boron based on this? So this is kind of what the AP test goes off of. It's like, tells you some information. It's really, really hard. So you're like thinking like, okay, it's one of the ones that are like super bonded together, nearly as hard as a diamond, okay. Super high melting point, but does not conduct electricity. So, I mean, I'm thinking network covalent. If you're still wondering like, well, why isn't it calcium oxide? Because if it's at room temperature, it's not hot enough to melt it, right? Correct. It says though that my element, if it's just elemental boron, it's boron on boron on boron on boron. Ionic solids, you have to have two different things, right? You have to have a positive cation and a negative anion. That's not going to happen when you've got boron on boron on boron on boron. The only two options that you can have, same, like this one is not same on same. So that's why I'm leaning over here for network covalent. So there you go, there's my logic. Consider these three ionic compounds, okay, ions, metal, non-metal bonded together. Which one of these is the strongest ionic bond? So first thing I'm going to do is look at the charges, because if we had something like Na and Cl together, 1 plus 1 minus, that's not as strong as 2 plus 2 minus. But they're all 2 plus 2 minus. So, okay, so not really helpful based on the charge. 2 plus 2 minus, 2 plus 2 minus, 2 plus 2 minus. The only other thing that I can think of that would be like similar is the distance between the core. So the closer that you get them, the more they're going to want to attract like magnets because they're opposite charges. So since they all have similar charges, I'm going to say, just looking at the lines here, I wish I had a ruler. I don't have a ruler. Makeshift ruler. Okay, from here to there. I think that one's the shortest. Shorter than that one, and shorter than that one. So that one has the shortest length between them. Since they're all the same charge, I'm going with this one. So make sure you explain that in your answer. If we had something like aluminum 3+ and nitrogen 3-, oh, for sure I'd pick that one because look at the charges, 3 versus 2. But that wasn't an option. Every single one of them was the same charges. So the only thing I looked at was the distance. Particle diagrams. The College Board's curriculum for AP Chemistry places a strong emphasis on conceptual understanding, including representations of particle phenomenon. Okay, that is teacher lingo for saying you will get pictures like this on the AP test and you have to figure out like what's going on. So similar to up here, we had to figure out from the picture that this one has stronger ionic bonds. You've got to analyze some pictures down here. So which type of solid is each diagram representing and how do you know? That's important. What parts of the image show this? Provide a rationale for each. So it's not as simple as just being like, oh, diamond. I memorized that diamond was network covalent solid. That doesn't really work. Like, you're right, it is a network covalent solid over here. But like, how do we know from the picture? And I would say from this picture, it is network covalent because like this is showing covalent bonds in every direction, as well as this, let's see, how do I draw this? I would say it's bonded in all directions, and network covalent is the only one that can do this kind of 3D net thing. That would be my rationale. The other ones, I'm really good at identifying this one because it's got that checkerboard, and the checkerboard, they want you to use the word lattice, but you can call it a checkerboard. The lattice of different elements that to me is showing an ionic solid. It also kind of has this like really, I don't know how else to describe it other than that checkerboard grid. Over here, this one is looking like a metallic solid to me. Specifically because the cation core, and this paper has really terrible printing, but all of these little things here say E-. That's how they're showing the C of electrons. Metallic solids are the only ones that have C of electrons in it. And last but not least, this would be the molecular solid. Rationale being each individual thing is bonded. That's bonded together. These two are bonded. But the whole structure is only held together by these IMFs. Use the particle representations to explain why graphite is so much softer than a diamond. So diamond is here, graphite is here. And this one we already talked about a little bit, right? They're both network covalent because they have a net system, net All of it's covalently bonded together. But this one, since it has a 2D structure instead of a 3D structure, this one can link to itself. This one does not link to itself super great on the different levels. So we have to have IMFs that come through to kind of sticky the two-dimensional shapes together. So make sure you explain that using the particle representations. It's kind of like I did, I labeled, and just put that in words. And the last one, on the AP test, you may need to draw particle diagrams. Most are easy, but network covalent solids like diamond can be tricky. Practice until you can do a reasonable freehand sketch in about 30 seconds. So here's some tips. So you're going to start out with just, let me get a new color. You're going to start out with kind of drawing them out in all directions. Once you have that, expand it out and take those sides and also expand it, but start linking backwards. So I would start by tracing these like I just did. And then over here, I want to see your best, your best attempt at drawing a network covalent solid, like a 3D one.